Good morning, everybody. I'm Rebecca Santamaria Fernandez, Director of Industry Partnerships and Commercialization Engineering at Imperial Enterprise, and I'm delighted to welcome you all today to our third Imperial.Tech.Pitch event, focusing on infrastructure resilience. With this event, which we're co-hosting with Imperial Business Partners, we're hoping to bring some of the amazing work that goes on at Imperial to your home offices and your workplaces. At Imperial, our mission is not just to understand the world, but to have an impact on it and to change it for the better. We're doing this through world-leading research and education, turning great academic thinking into impactful innovations. At Enterprise, we support Imperial staff and students on their enterprising journey, and we connect them to businesses like yours. We are passionate about developing and commercializing Imperial's academic discoveries, and impact is really at the heart of what we do. Today, I'm truly hoping that we can give you a snapshot of Imperial's engineering research and capabilities and amazing technologies that are addressing critical elements across different aspects of infrastructure resilience. You'll hear some examples where we're providing solutions to reinforce infrastructure systems, but also social and community resilience. These are massive challenges and we cannot face them alone, and we need you and your organization to help us change the world. In a few seconds, you're going to meet my colleague, Professor Washington Ochieng. Washington is co-director of the Institute for Security Science and Technology here at Imperial, and he'll tell you a bit more about how we're tackling these challenges. Then we've lined up 6 awesome speakers that will showcase our research capabilities and technologies available for licensing in this space. And right after the pitches, you'll have time for questions at the Q&A chaired by Washington. And I would encourage you now to submit your questions or comments in the chat function so that we can pick this up during the Q&A. And of course, after the event, our team will be more than happy to follow up with you, help you get access to our researchers and inventors, but also to understand a little better or get more information about the research and technologies and how this might be relevant to you. Contact details are in the event page or in the chat. And with this, please enjoy the event, and I'll now hand over to Washington.
Thank you very much, Rebecca. Good morning, all. My name is Professor Washington Yoto Ochieng. I am the head of the Center for Transport Studies in the Department of Civil and Environmental Engineering. I'm also the co-director of the Institute for Security, Science and Technology at Imperial College London. It is my absolute pleasure to chair this meeting today. Now, COVID has given us an X-ray vision to our critical infrastructure, its strengths and weaknesses. Now, whatever the threat that our infrastructure faces, whether that's biological, social, environmental, cyber, physical, and their interactions, I think it's time now to look quite critically at acquiring our new infrastructure and retrofitting the existing ones to deliver a maximum level of societal resilience. Now, doing that requires us to achieve the same level in terms of our infrastructure resilience. So a key priority for us is to ensure that we create impact, and to achieve that we want to partner with industry, government, non-governmental organizations, and even the public to make sure that our research is informed and is translated into effective solutions for industry. Now, today, the talks will give you an insight into some of our fascinating and crucially important research, innovation and technologies currently being developed at Imperial College London to enable us to address some of the challenges that will emerge today and reinforce infrastructure systems, core networks, and social and community resilience. We will discuss different aspects of infrastructure resilience, from digital and human characteristic systems, Internet of Things environments, and materials for a greater and more resilient construction, unveiling solutions to minimize the impact of disruptive events. I very much look forward to hosting an interesting Q&A discussion after the pitches. Please may I remind you to submit your questions in the chat, and we'll do our best to address them. And now, without further ado, it is time for our first pitch. Thank you very much indeed. Thank you.
Hello, my name is Dr. Ana Mijic. I'm a senior lecturer in water systems integration in the Department of Civil and Environmental Engineering, and I am a co-director of the Center for Systems Engineering and Innovation. In the next couple of minutes, I will tell you about our work on systems approaches to water infrastructure resilience. So to set the scene, I would like to talk about the challenges of the integrated planning in the water sector in the UK. And the example I have shown is presented here, and that is the challenge of planning of the water resources for an urban environment, which is done through the water resources management planning. But also then the second part of the system, which is linked to the planning of the drainage and wastewater resources through the drainage and wastewater management plans. So these two plans are currently done separately. The models that are used for their evaluation are also the separate models. And the question arises, what are the errors in the predictions and the opportunities we miss because we are not doing the integrated approach? To address this, we have created a CityWatt model. It's an urban scale model which simulates the water infrastructure in a holistic way. So it simulates supply and the wastewater side of the system. It also simulates the consumption, and it also simulates the interaction with the environment. So we can model the flow and the pollution propagation through the system, as well as the in-river water quality. And what is really novel about this model is that it's a very flexible framework. So each of these components can be modeled separately, and each of these components can have different levels of complexity. And that is computationally very efficient framework. The model has been developed as part of the Camellia Impact Program. So a few things we can do with the model and how we are using the model to look at the resilience. Once we have the integrated view of the system, we can also then look how system components are connected, and we can also look at the range of interventions and how their impact propagates through the system. Why this is very useful for water companies is that they can now look at the range of intervention options, both on the supply and the wastewater side, across a range of indicators, which are again operational indicators such as supply matrix, but also environmental indicators such as, in this case, in river water quality. And then we can capture the co-benefits, as for example, you see here for options such as demand reduction, but we can also capture unintended consequences. So where the system is fragile for the future interventions, such as the impact of the wastewater reuse, negative impact on the river water quality. Then we can also look with this type of model at the implications of different demand scenarios. And here you see the work that we have done to look at the COVID-19 water changes in the water demand. We have done that by simulating in much more detail demand scenarios, looking at the role of appliances, but also commuter flows. And with such generator, we can now propagate that impact through the whole system to look at changes in the flow and the range of water quality indicators across the city as a whole, and then look at the vulnerabilities in the system. For example, we see that smaller rivers such as River Lee is more sensitive to changes in the water demand scenarios under COVID than River Thames. And then finally, what we can do with the model is to look at the future scenarios. So we can force the model with a range of climate simulations, and then we can see future changes. So here we see the results for the baseline green, near future blue, and far future in red scenarios. And we can look at the indicators such as, again, river water quality. We can see the increased risk, so increased pollution concentration in the future, but we can also see the ways how we can influence or intervene in the system, such as in this case, the role of obstruction licenses, so environmental law. And where we want to go in next is really taking the modeling to the next level through a concept of water digital twin. The twin aspect here is really important because we believe that we have a model that is realistic representation of the water system, and if such model would be adding the visual interface, such model would be applicable for the stakeholders to have a direct use, to simulate a range of options, to visualize the results, and use that to make decisions. We see the real value of the tools such as CityWatt. So that is all from me. Thank you very much, and I'm very much looking forward to the discussion. Thank you.
Hello, my name is Dr. Stella Pedrazzini. I'm a lecturer in Engineering Alloys and Metallurgy at Imperial College London, and I run a research group working on corrosion. So today we're going to be talking about tackling corrosion to improve sustainability. And my contact details are available at the bottom of the slide for anyone who needs them. So let's start with a little bit about me. I studied material science at Trinity College, Oxford, stayed on to do a PhD, also in material science, and then carried on in academia as a researcher. 3 years at the University of Oxford, specializing in aerospace and nuclear materials, and then 2 years at the University of Cambridge, working specifically on aerospace and corrosion. And then I moved to Imperial College in 2018 as a lecturer in engineering alloys and started the research group on corrosion. Last year, I was awarded an EPSRC Early Career Fellowship and a Royal Academy of Engineering Associate Research Fellowship to further this work on corrosion, which is a 5-year research plan. Corrosion is a big issue. Corrosion, the NACE, National Association of Corrosion Engineers, estimated the cost of corrosion is $2.5 trillion annually. This is a 2016 estimate, obviously going up. And this is 3.4% of the global GDP. It's a huge cost. And also, they've identified the need for more corrosion management professionals given the wave of retirements coming up. And a lot of these retirements have happened. So there is a distinct lack of expertise and a need for more people to work on this very important issue. Now, corrosion comes with two issues. One is cost, and the other one is potentially safety. And these are some examples of headlines that have come up recently in newspapers outlining the issues with safety. There are plenty more. These are just a selected few. Which is why my EPSRC Early Career Fellowship and Royal Academy of Engineering Associate Research Fellowship came along. This is a 5-year research plan, dividing this into 4 different main categories. So there's oxidation, corrosion, coatings, and contamination. Most metals oxidize, and the oxide layer on the surface is the first line of protection from corrosion, which is why we need to look at oxidation as well. Corrosion involves replicating surface damage. So these metals can be in cars, planes, buildings, wherever, and they get exposed to a different environment, and we need to be able to replicate that environment in our lab to test them. And then coatings, some of them are coated. This is more specifically for aerospace, and the coatings can be inert, but usually they're far from inert, and they can be a catalyst for corrosion, especially when scratched. And then contamination is the 4th part, so adhesion of contaminants as they go on the surface, which is why over the last few years at Imperial College, myself and a few colleagues have been building up the capabilities to work on corrosion. So we have alloy production facilities, we can make our own alloys, and we have characterization facilities. We've just received one big grant from EPSRC to study where each individual atoms go, which helps us explain the mechanisms behind corrosion. And also in my group, we have been building specific equipment, so autoclaves and corrosion fatigue testing rigs that can run different gases at different pressure and water vapor and track the temperature very accurately. Facility that we have is called the cryo-EPS facility, and it will involve interconnected atom probe, TEM, and a focused ion beam microscope.
Hello, my name is Emil Lupu, and I lead the Resilient Information Systems Security Group in the Department of Computing. I would like to share with you today some of the work that we are doing and some of the challenges that we seek to address. Resilience to us has a very specific meaning. It means resilience to an adversary that deliberately tries to compromise the system and interfere with its operation. The question that drives most of our work is really quite simple. Systems are going to be compromised, and yet they need to be available. How can we then design systems that can operate safely even when they have been partially compromised? And this question is particularly pertinent in the case of infrastructure, where availability is key. I would like to focus on two specific aspects today: data spoofing and minimizing system downtime. When an adversary has compromised a part of the system, they can spoof the data that is being reported in order to alter our perception of reality, to make us believe that events have happened when they actually haven't, or in order to mask events that have actually happened. We have designed new anomaly detection algorithms in order to detect malicious data injections and identify the sensors that have been most likely compromised. But we have also designed new methods in order to evaluate the risk tolerance of the sensor network. In other words, how many sensors would an attacker need to compromise? And as you can see in the lower part of this slide, in order to evade our anomaly detection algorithm, that number is quite significant. Increasingly, we use AI and machine learning as part of our infrastructure. An adversary that can do data spoofing can use this in order to exploit the vulnerabilities in machine learning algorithms. In our work, we have shown that it is quite easy and without any knowledge of the system to design data perturbations that enable an attacker to evade detection and classification on a large part of the input set, as you can see in the top part of the slide. We have also shown that it is possible to efficiently calculate optimal poisoning points, or even train AI algorithms in order to generate poisoning points with different levels of detectability. This is particularly useful to test the robustness to poisoning of machine learning algorithms. To ensure the resilience of a system, different strategies can be adopted, as illustrated in the diagram in the top left-hand figure. We can improve the robustness of the system. We can increase the redundancy in the system in order to be able to delay the effects of the attack, or we can facilitate the recovery of the system. How can we choose between these different strategies? In order to choose amongst them, it is not sufficient to focus only on the attack, but one must combine models of attack progression with models of system functionality in order to reason about the impact of the attack on the system and the resilience under different attack scenarios and different models of cost. We use attack graphs in order to model the progression of an attacker through the system, as they allow us to reason about the probability of compromise to other parts of the system when some parts of the system have been compromised, in particular through Bayesian attack graphs. And we have shown in our work that Bayesian inference on attack graphs can scale to systems of a reasonable size. Considering models of attack progression together with a service dependency model enables us to reason about the cost impact and about the cost of different response strategies. Our work shows that it is sometimes more cost-effective to favor recovery over containment, and that considering long-term costs is important, especially when there is a delay between the moment when the compromise occurs and the moment when it is detected. Considering models of attack progression together with service level agreements and performance model of the system, our work has shown that there are clear cutoff points when redundancy is beneficial, that new metrics are needed in order to help track the balance of different types of costs, and that it is difficult to predict how parameters impact results. So tools are needed in order to support this type of analysis. Our work also combines security with safety. We apply safety analysis in order to identify which circumstances can lead to hazards and safety violations, and then identify attack paths that enable an attacker to trigger those situations. But much work remains to be done. New tools and methodologies are needed to design systems that can degrade gracefully and preserve operation even when they have been partially compromised. We are keen on new collaboration to address these challenges. Thank you.
Thank you very much, Anna, Stella, and Emil, for your great contribution. I'm Garrett Boon, and I work with Rebecca in the Industry Partnerships and Commercialization team at Imperial. I hope you are enjoying the event today. If you want to know more about what was discussed today, and you are interested to engage with our academics and get access to our technologies, please get in touch after the event. All details are posted in the chat. Unfortunately, we will not have time right now for any questions, but please keep on posting your questions or comments in the chat, and we will pick them up during the Q&A session. And now, let's continue our event and hear more from our researchers and inventors about the amazing technologies they are working on.
Hello, my name is Bob Shorten, and I'd like to talk about something a little bit different. I'd like to talk about the need for digital infrastructures that are robust and resilient, that can be used to enable not only new disruptive business models, but also to empower citizens to make good choices and to empower personal responsibility. So the title of my talk is Infrastructures for Choice, Responsibility and Disruption. My background is from smart cities and smart mobility and more generally IoT. The traditional IoT narrative is one of connectivity, enabling devices to become connected with each other, with people. But there's an alternative IoT narrative, and that is actually using that connectivity to manage the natural connectivity that exists in society. After all, we're already connected to each other through the air that we breathe, to the energy that we consume, to the data that we generate. And, you know, a consequence of COVID is that we now all realize how important it is to manage that connectivity. So the IoT narrative is changing from one of enabling devices to become more and more connected to exploiting this connectedness to enable personalized choice and responsibility in society. And the need for this managing of connectivity is evident. There are many examples. There are many use cases where we want to do that. One such example is in the area of automotive-induced pollution. You know, traditionally we think of making devices cleaner and cleaner. However, if the growth in the vehicle number outpaces the rate at which devices become cleaner, then actually the aggregate effect of this can be even poorer air quality, even though devices have become cleaner. And this actually graph in the bottom corner of the slide depicts that, exactly that, from my hometown in Dublin between 1998 and 2007. And this is true also of electric vehicles. Electric vehicles have tires. Tires wear. Tire particles are a form of pollution. And the more and more vehicles we have in our cities, the worse this is going to become. So even for with electric vehicles and zero tailpipe emissions vehicles, there's a need to manage this connectivity. There are many other examples. When we design social contracts to sort waste, there's a need for personalized interventions, for personalized deposits. And the same is true of the many disruptive business models that are emerging right now, where we need to reimagine new forms of ownership, which is also enabled by digital infrastructure. Two such examples are the sharing economy. When we share devices now, we need to be able to rapidly transfer ownership of those devices from one person to another. And this is a very complex thing, mainly because physical devices such as cars, have transitioned from being purely physical devices to being cyber-physical devices. They generate data as well as being physical devices. So establishing and transfer of ownership of such devices, especially when you want to do it rapidly, is very complicated. The same is true in the circular economy. Servitization and servitized sharing is a very important tool when it comes to the circular economy. The same type of ideas, the same type of need to reimagine ownership arises in that context. So what do? We're interested in building these infrastructures to enable cyber-physical assets to be servitized and to be shared. Our work is built on three notions: digital identity, new ownership models, and the need for compliance. And the type of businesses that we're interested in enabling are ones based on ethical business models, ones where machines trade services and resources with other machines or with humans, and we're also interested in enabling and empowering the circular economy. Thank you very much.
Hello, my name is Barney Shanks from the Department of Civil and Environmental Engineering, and this is my partner, Sam Draper. Together, we founded Seratech with one simple aim: to fully decarbonize one of the most polluting industries on the planet, cement. Due to our massive global consumption of concrete, the cement industry contributes a total of 8% of all human CO2 emissions. Despite this, infrastructure remains vitally important, and simply building less is not a viable solution to mitigate these emissions. It is especially true since the effects of climate change will render a significant amount of our infrastructure no longer fit for purpose and in need of extensive retrofitting or even complete rebuilding. This is even more of an issue in less economically developed countries. Not only are these countries more likely to be affected by climate change, but their existing infrastructure is in the greatest need of development, with no future planning originally built in. Couple this with rapidly growing populations, and the demand for new infrastructure and materials is colossal, with the developing world accounting for 90% of future cement production. Developing sustainable infrastructure is a legitimate need for all nations, and low-carbon materials are vital to achieving this without furthering the climate crisis. Current low-carbon cements cannot promise carbon neutral and rely on byproducts from industries such as steel production and coal-fired power stations. The imminent decarbonisation and reduction in size of these raises serious questions over the long-term viability of these solutions. Our solution is technically very simple and uses only basic processing equipment and widely available raw materials, allowing it to be deployed in any country around the world. Seratech permanently sequesters CO2 during our production process, preventing it from ever being emitted into the atmosphere. This process involves extracting a reactive silica from a naturally abundant ultramafic rock and sequestering the CO2 in the byproduct. The silica can then be blended with Portland cement to form a carbon-neutral composite from which concretes can be produced. This composite cement is already covered by European standards, so it can be implemented immediately. Furthermore, our product is compatible with Portland cement rather than competing against it. This means we can deliver radical changes without rendering trillions of dollars of existing infrastructure obsolete. This technology has been proven at lab scale. We're exploring routes to collaboration with industrial partners in different sectors with the aim of upscaling production to tons of carbon-neutral concrete per day and conduct some trial pours to assess the performance of the material versus current Portland cement concretes and other low-carbon technologies. The potential of this technology is huge. This is the first carbon-negative cement that can be delivered on a global scale. As such, it could single-handedly prevent almost 3 billion tons of CO2 from being released into the atmosphere each year and completely decarbonize the cement industry. This has a massive impact on infrastructure resilience in a number of ways. Most importantly, any zero-carbon material allows new infrastructure to be designed and delivered with future use considered. You can use a bit more material here and there to give that flexibility without having to worry about meeting carbon targets. A solution such as this, which jumps straight from the current position to carbon negative, also improves the resilience of the cement industry itself. Not only does our technology give the construction industry agency to mitigate its own emissions, rather than relying on other technologies such as carbon capture and storage, but also provides some certainty and consistency in how the industry will produce and deliver cement in the long term. Thank you for your attention, and I look forward to your questions later. If you would like any further information, please do contact us via the email addresses on screen.
My name is Mohammad Heggo. I'm a research associate from the computing department of Imperial College, and I'm here to present our newly innovative technology CogniSense, which is a radio frequency non-intrusive monitoring technology that's used to monitor the rotation speed and the vibration of rotating machines. So the condition monitoring market size is expected to reach around $4 billion by 2025. And the reason behind that is the ability of the predictive maintenance techniques and the condition monitoring techniques to outlaw inefficient machine systems, and hence can increase the machine productivity. However, the traditional condition monitoring techniques relies on many sensor types that requires installations on the machine body. This installation of the sensor or the reflective tape on the machine body interrupts the machine nominal operation, which is considered as a huge disadvantage in the current condition monitoring techniques. So if, for example, if we take a look over the mechanical tachometer, the optical tachometer, the magnetic sensors, or the vibration sensors, all of these types of sensors require either installation of the sensor on the machine body or installation of a reflective tape on the machine body, which interrupts the machine nominal operation. Actually, the cost of replacing the vibration or the rotation speed sensor is expected to be around $3 billion in 2020 and to be around $5 billion in 2027, which is a huge amount of cost. And it's not just the cost of replacing the vibration or the speed sensor, but it's the cost of the machine downtime. Because the machine downtime average cost for all the types of industry is ranging between around 160K per hour to around 260K per hour. And in the automotive industry, it's even higher. It can reach up to $3 million per hour. So CogniSense presents a non-intrusive way for monitoring the rotating machines through using the radio frequency. For example, CogniSense can decrease the machine stoppage hours required for installation of the sensor or reflective tape on the body of the machine. CogniSense can support also non-line of sight monitoring for the machine, so it can monitor the machine safely inside its case without even opening the enclosure of the machine or having to interrupt the machine nominal operation. CogniSense can also monitor multiple rotating machines on the same time. The main principle behind the CogniSense relies on the interaction with the electromagnetic waves. So we actually send our specific types of electromagnetic waves. These specific types of electromagnetic waves interact with the machine, then we receive them back, and then we begin to analyze the received electromagnetic waves from the machine. And through using efficient signal processing techniques, we can interpret the machine vibration frequency or the machine rotation speed frequency. We have tested CogniSense over several and different types of the machines, and we have achieved in all of these types of the machines around 99% of accuracy in the obtained results. For example, if we take this ultra-low temperature freezer and we want to monitor the speed of the inside fan, it's actually undetectable by the current of the shelf tachometers or the current of the shelf monitoring techniques. However, using CogniSense, we can monitor its rotation speed efficiently with time. CogniSense is currently patented technology, but however, we are looking to increase our industrial deployment through creating more industrial partnership. Thank you for your listening, and I'm waiting for your question.
Thank you, Robert, Barney, and Mohammad for interesting research and technologies. I am Lora Fernandez, and I support the commercialization of Imperial's technology. I hope you are all enjoying this event on infrastructure resilience. I will encourage you to visit Imperial.Tech, our technology licensing website, where you can find the technologies available for licensing and get in touch with our team. It is now time for the Q&A. Please keep posting your questions in the chat. Without further ado, I shall now leave the floor to Professor Washington again.
Thank you very much indeed, Laura, for that. It's been truly inspiring, even from my own perspective, listening to the great work that is happening at Imperial College London. And there is more. That's just a sample of what goes on at this university. So thank you all from around the world, from wherever you are joining us this morning. I had prepared one or two general questions to start the Q&A session with, but actually that has now been superseded by the questions coming on the Q&A, which obviously encapsulate some of the thinking I had. So my first question, which combines a couple from our delegates, is to do with the meaning of infrastructure resilience, its dimensions, whether it differs for different industries, and if it should include decarbonization. So over to my colleagues, answer all of the question or a part of the question, as you see fit.
Shall I start, Washington? Would that be
Yes, please.
okay? Yeah. So I mean, I think traditionally, when one thinks of infrastructure resilience, one thinks of robustness to failure. But actually, I think, at least in my opinion, resilience, when we talk about infrastructure, is more about the ability of infrastructure to absorb shocks. And of course, shocks may come in the form of damage and failure. But also, as Emil said, the shocks can be introduced to adversaries trying to disrupt the infrastructure, but they can also be due to new business models. Particularly when you're talking about digital infrastructure, is the infrastructure malleable and adaptable enough to accommodate new business models? And that's something that's really important going forward now as we embrace notions around circularity and the sharing economy, and even robustness with respect to policy changes. There is a basic right of access to infrastructure for citizens, and of course, when we introduce new policies from a regulatory perspective, one has to ask, are we infringing the rights of access for basic rights of access for citizens and for businesses? A great example of that would be road pricing. When we introduce road pricing, we do it with the best of intentions to reduce emissions or to manage congestion. But we do disenfranchise sometimes the most vulnerable in society, the people that are least ability to pay road pricing, and of course it has no effect for very wealthy people in society. So the issue of resilience, I think, or the topic of resilience, certainly has many dimensions. I've just mentioned 4 of them there. I'm sure there are many others, and I think as we develop infrastructure, we need to have a broader view of what resilience means as we go forward.
And so the question of whether it changes for different industries, it requires that dialogue that you're talking about, Bob. And that's one of the reasons why we are having this meeting today, to get the stakeholders together to agree on things like that. Who would like to go next, please?
Happy to go next, Washington.
Thank you.
And I think, from my point of view, which I think goes very much along the lines that Bob has mentioned earlier, to me, resilience is essentially the loss of service over time due to a certain perturbation. Now, whether the perturbation is failure, whether the perturbation is essentially a malicious adversary, whether the perturbation is actually disruptive technological change, or whether the perturbation are sort of disruptive changes in demand, those are effectively different causes which lead to a perturbation. I think it's not just about the ability to be robust to the perturbation, so to resist the perturbation, but it's also about the ability to recover very, very quickly and recover the functionality that is provided by the infrastructure, in particular in the case of infrastructures. I think it has multiple dimensions. There is a sort of physical dimension, and we've heard talks about essentially degradation of the physical infrastructure. It's got a digital infrastructure sort of dimension, and it's got a societal infrastructure, a societal sort of dimension as well. In terms of the different industries, I think that within this sort of definition, the definition kind of is agnostic to the type of industry that it is. But I think that different industries have a slightly different context, whether it's technological context, whether it is market context, whether it is regulatory context. But I think we also should not forget that, especially in terms of infrastructure, there isn't sort of, the different infrastructures are interdependent as well. So I think that needs to be taken into account.
Thank you, Emil. Ana, does resilience include net zero?
Well, it does, isn't it? Maybe I would like to add a couple of aspects of the resilience. I think the way we see the infrastructure resilience in the Center for Systems Engineering is really about the adaptation capacity. And I think we've mentioned that in some of the presentations today, because one thing is to predict the resilience, but then the other one is, can the system change to be able to cope and achieve that security that Emil has mentioned. The other aspect is, I think, really important one is about the interdependencies. And I think also something that Bob has mentioned around the aggregation effect, because our individual systems may be resilient in some shape or form. I think something around the sustainable materials is a really good example. So we may come up with the very good materials which will save all the carbon, but if we keep building and keep using that infrastructure in the same way as we are doing now, nothing fundamentally will change. We'll just shift the burden or shift the problem somewhere else. And then I guess my final point is around the digital element and the kind of role of tools and predictive tools and monitoring to be able, for us to be adaptive, to basically track the change in the system and be ready to react and adjust the system to be more resilient. Again, the way how infrastructure currently is designed is very inflexible. And I think there's lots of thinking around that going into the future, how we can enable those systems to, change quickly the functions, readjust, and spread the risk
Yes.
across the system.
Very interesting. Just a question for you, a follow-up question for you, Ana. How do you integrate everything that colleagues have talked about? You talked about the integration challenge. Tell us about that.
Yeah. There are a couple of ways, I think, of doing that. So we have started doing the integration, what I mentioned in the water system. So to basically integrate the wastewater and environmental quality, okay, which is physically connected, but it's not connected within the models. For that, we had to sacrifice the complexity of the models, okay, but we did that sacrifice very consciously, and we are using the model for the certain application. So it's a very fast model, and it can do what if scenarios. We wouldn't use it for a detailed design. What I think is possible to be done on the platform such as that one is to keep adding other aspects of the infrastructure sectors where there are significant interactions, okay? We mentioned the human behavior element, and I think the use of infrastructure, if we cannot predict the use of infrastructure, we'll never achieve the resilience. That's my opinion personally. So kind of going into simplifying of the models which expand the boundaries of the simulation and can do what if scenarios under range of stresses, being it a climate change or any other change in the system, and seeing where are those interdependencies and especially feedbacks. So, not to fix one bit, but make something else worse.
Thanks very much, Ana. Corrosion, Stella. A very technical one, talking about atoms and things. What does the atom probe tell you that you couldn't know without it?
That's a very good question. Atom probe is a technique that's not very widely used, and there are very few in the world. And now that we've got one at Imperial, it's opening up a lot of doors for research. So atom probe will give us a 3D atomic scale reconstruction of what's going on at, for example, a crack tip. So if you have some failing infrastructure, for example, steel beams that are corroding, you can figure out exactly the mechanism for corrosion by analyzing the mode of failure. So that combined with all the other infrastructure that we're getting for Imperial is going to definitely open up some new avenues for projects. And also with atom probe, you really need to know the question that you're asking. So a lot of times people tend to throw every technique at a problem and figure out which one will work best. Whereas with atom probe, if you have a really specific question in mind about the mode of failure, that will be able to give an answer. And also that answer can then be fed back into either designing a more resilient alloy or coatings or developing a way to protect the infrastructure.
So how do you see yourself working with the delegates here to deliver that great job that you're doing, the great work? How do you work with the delegates?
Well, we all have very different expertise, but it fits in many different ways. There are different aspects to resilience of infrastructure, and I think we've covered a few of them. I definitely agree with Emil's definition that resilience, for me, it's about minimizing service disruption. And that can mean either quick replacement or extending component lifetime or a whole variety of different methods for either preventing failure or bouncing back from a failure relatively quickly. So I can definitely see my work fitting in. There's also an aspect of making everything more easy to recycle or extending component lifetime to minimize carbon output. So yeah, there's definitely a lot of different aspects, and materials fits in with policy, with a whole variety of different aspects.
Thanks very much, Stella. Barney, that was quite exciting, what you're doing. Really, really exciting. So there's a question here, which is buildings. Let's say they use cement today. What are we going to do? Are we going to rebuild them with your new cement? How do we retrofit? What would be your view on that?
Well, I think obviously you can't demolish existing buildings to rebuild them with carbon neutral cement. That sort of defeats the purpose. But there's so much more building to do in less economically developed parts of the world. And so I think they're the ones that are at most risk from extreme weather and severe weather. So there's a lot of intense infrastructure building that needs to go on there. And that's sort of where, you look at somewhere, I don't know, say India, where their cement production is just increasing and increasing. If you can marry that with a low carbon technology, then that's where you might see the greatest impacts.
Thanks, Barney. Mohammad, there's a lot of clutter, signal clutter around, electromagnetic induction and so on. One of the questions is, how do you filter all of that in your sensing without sensors?
Okay, so I think our signal, we name it, it's our special signal. So we are not using like any of the off-the-shelf antennas that are available in the market. We design our own antenna. So we design our own signal. So this signal has some special characteristics which characterize it from the surrounding signal. So for example, if we are working in the Wi-Fi band, which is normally used nowadays for everything, we can characterize our signal because it has special features, it has special characteristics, frequencies, bandwidth, amplitude, everything. So we know our signal specifically, and we can extract it outside from the surrounding noise, which can interrupt our signal. This is the first thing. The second thing, that our antennas just is really directive. So it directs our signal towards the required machine and is not affected by the surrounding. So it doesn't pick up like noises from the surroundings because it's just directive. It just expect the signal to be received from a certain direction, which is the direction of the machine itself. So these are some sample types of signal processing. Behind the lines, we have other signal processing techniques which can deal with the noise and extract the signal from the surrounding noise. So this is something that we have tested inside our labs and inside the machines that we have tested already.
Thank you, very interesting. And Bob, there's a question about the role of human factors in managing connectivity. The question is, are you treating that with the same level of criticality as you would the other aspects of infrastructure?
I think we are. I think one of the roles that a digital infrastructure can play is to empower what we call personalized interventions. When we think about, for example, pricing signals, again, they're very crude instruments that apply to everybody. And I think there's an opportunity now, when you look at new technologies like distributed ledgers, like blockchain, for example, but there are other ones where, you know, we can empower, you know, not only new notions of ownership and identity, but also, you know, make people responsible for their own personal choices and the consequences of those choices. So we can, I think for the very first time, we can really move towards what we might call a polluter pays model, you know, where if you pollute, you pay for it. And if you don't pollute, then you don't pay as much. And I think those type of tools, I think, are going to become more and more important as we, you know, as we go forward. I mean, it's really clear in the context of COVID how important are the need for such tools, you know, when you try to enforce things like mask compliance.
Yeah.
You know, they're very, very important. And I think for the first time, there's an opportunity to realize some of those technologies.
Thank you. I've got a couple of general questions on here, but before that, let me ask Emil. There's a question about your detector, your detection algorithm. Does it detect any type of failure manifestation, or is it for specific failures, or at least manifestation of failures?
Yeah, so effectively, that's about the sort of the anomaly detection for malicious data injections. We don't make specific assumptions about the type of sensor. So we have applied this for example, for temperature sensors, for volcanic eruptions, for medical sensors. The assumptions we do make are that the sensors measure the sort of the same type of value. So they all measure, for example, temperatures or vibrations and so on, that they are all essentially measuring a physical phenomena which has manifestation across multiple different sensors, so which is witnessed by multiple different sensors. And then that effectively events, so, you know, a fire or something else, is something that has a sort of clear threshold of detection. So we don't make assumptions about the type of anomaly. What we do is that we look at the correlations that we expect between the various sensors, and we effectively then analyze disruptions to those correlations. Yeah. That's a kind of the short version, but I'm happy to sort of give more details in an offline discussion.
Thanks very much, Emil. So we are coming to the end of the Q&A, and we have a very interesting question, which is a fitting question to the end of Q&A. And I'm going to ask the panel members to just half a minute, if not less, to give us your view on it. So the question is, the attendee would like to ask the panel to share your view in working with industry and how Imperial can provide informed decisions, but not influenced by the company's goals. So how do you provide informed advice without necessarily being biased by the goals of a particular industry? So the question is, how do we best work with industry? And Bob, you can kick off. And I would ask each and every member of the panel to share their view on this one before we close.
Well, I think personally, I think you need to try and look beyond the needs of any one company. You know, it's a prediction task, really. You know, you're trying to predict where the threats, where the opportunities, where the needs are going to come from, and you try and address that. I think sometimes working with companies can help that, because it can sharpen your thinking, it can help your decision making. But I think you need to sort of see beyond the needs of any one company and any one industry when you're formulating research goals and research plans, and try and think about the problem in an agnostic way, and you know, act without bias and be honest in reporting what you find and what you think.
Yeah. Thanks, Bob. Barney.
Yeah, I mean, so for us working with industry, you know, of course, we're trying to do something that maybe they're not totally 100% in line with in their own goals. And you've got to say, look, maybe take a holistic approach to, well, humanity sounds a bit grandiose, but sometimes industry are, you know, resistant to the changes in the sort of direction that we're trying to get to. So it's just important in working together and showing that in the long term, it can be beneficial for everyone. And especially if you can get, big players involved, then that's the sort of direction that you would want to take.
So it's a win-win situation.
Exactly, yeah.
Emil?
So most often I find that we tend to work on sort of more generic problems rather than the specific problems of a particular company. But we tend to work very, very often with industry, and to have a dialogue with industry, because first of all, it offers a sort of an opportunity for impact of the research results, and seeing them sort of deployed and applied in practice. We're not just doing research for the sake of doing research, but ideally we would like to sort of for the research to actually change the way and make in the way in which systems are used, and change the design of those systems to make them more robust, and to make them more resilient.
Yeah.
In terms of collaborations with companies, I have found it varies quite a lot depending on the company, because companies tend to vary a lot in their sort of appetite to engage with research, in the way in which they would like to work with universities. So we're trying to sort of to be flexible and to offer different modes of engagements to do different things.
Thanks, Emil. Time has caught up with us, I'm afraid. We can obviously continue this discussion. That's the idea. We started, we continue. So I'd like to hand over to Julia to close the meeting. So thank you very much indeed, everyone. Thank you.
Thank you, Washington. My name is Julia Zanghieri, and I work for the Imperial Business Partners team. I'd like to thank Washington and all the panels for their very interesting conversations and comments, and I hope this has inspired our audience to come back for more. And in this spirit, I'd like to thank audience for their time listening to us, and to go to our feedback form to help us improve the way we deliver these events, but also reach out to continue discussion for a joint innovation journey together with enterprise and the wider Imperial innovation ecosystem. Once again, thank you for your time, and we'll hope to see you soon.